Okay, so recall from last time that we say okay, so recall from last time that we say a surjective map Q from X to Y is a quotient map if Q inverse of U open implies U is open for U subset of Y. So some related definitions. So the main question we want to address right now in this section is, well, how to tell if a map is a quotient map. So we're going to prove some general facts which make this actually a quite reasonable thing. But before that, let me give you a couple more definitions. So we say a map X to Y is open if U in X open implies the image of U is also open in here in Y. Okay, so F sends open sets to open sets. And similarly, if we replace closed, open with closed everywhere, a map is closed if A in X closed implies F of A in Y is closed. Okay, so continuity is about pre-images of closed sets, and these definitions about, or of closed or open sets, and these definitions about images. Okay, so for example, let's see an example. Let's consider the projection map from R2 to R, which just sends a pair XY to X. So first of all, I claim that P is not closed. So to see this, we need to find some closed set so that when we project it onto the x-axis, it's no longer closed. In a picture, oops, closed. Well, here's an example. You take the graph of 1 over x, which is a closed set, but then when you project it, you get this open interval of the real line. So if we take A is x comma 1 over x, x not equal to 0, in R2, this is closed. It's not so hard to show using continuity of 1 over x. Does this follow from a homework assignment? Perhaps. Can't remember which direction. Okay, anyway, but the image P of A is R minus 0 in R, which is not closed. Okay. On the other hand, P is an open map. And to see this, it suffices to check on a basis of R2. For example, well, there's different choice of bases. We could use open rectangles. And well, if we choose open rectangles, then this is not so hard to see, since, well, if we have a rectangle AB times CD, then the projection of this, well, is exactly AB, which is open. Okay, and then for a basis, that means any open set is a union of open rectangles, and so then when you project, you get a union of open things, which is open. Okay, so that's the example. Oh no, sorry. Right, so now a proposition. So let's fix f from x to y, surjective. So if f is either open or closed, then f is a quotient map. So this is a condition, a sufficient condition to know that something is a quotient map. So let's prove this. So let's do the case f is open. The case f is closed is similar. So let's assume f is open. Right, so we want to show f is a quotient map. So let's fix W. So the definition here, let's remember here. Yeah, so let's fix W a subset of Y, and such that f inverse of W is open. And we want to show that W is open. Well, so f is an open map implies that the image of f inverse of W is open. But this is exactly W because f is surjective. Okay, so then W is open. So that's the argument. So I have a picture in my notes. Let me draw this picture. So that explains this equality. Why f on the preimage of W is W. So here's a little schematic. So we have Y and here's W inside. And well, let's suppose we're in a situation where X is not surjective. So in general, f of X is some subset of Y. So something like this. And well, if f is not surjective, then well, f inverse of W. So this expression here, these are this is exactly things in W which are in the image of f. So this here little piece, this is f of F inverse of W. And this could be a proper subset of W if F is not surjective. But of course, if F is surjective, then this is all of W. Okay. Right. So the case F is closed, I'll leave for you as an exercise. It's a good exercise to do. Okay, and then, so as a corollary of this proposition, this gives us what will be an easy test for a space or a map being a quotient map. So if X is compact and Y is Hausdorff, then any surjective map is a quotient map. So all you need to know is surjectivity to be a quotient map. And surjectivity, that should be something that is easy to check once you have a description of the map. So let's prove this. So this is a corollary of the proposition because, so what we'll do, so by the proposition, it suffices to show that F is closed. So let's fix A in X closed. And now this is going to happen. This is going to be pretty quick using some things we've shown already. So A closed implies that A is compact because X is compact. A closed subset of a compact set is compact. And then that implies that F of A is compact. We proved that the image of compact sets are compact. And then this implies F of A is closed because Y, so this uses that Y is Hausdorff. We prove that compact sets, subsets of Hausdorff spaces are closed. And then that's it. So we proved A closed implies F of A is closed, so F is a closed map. Okay, so this is really good. So now let me sort of remind you why we care about quotient maps. So this is for identifying quotient spaces. So the setup here, so we have X, some space, and P is a partition on X. So a union of, or P is a collection of subsets of X, they're disjoint, and their union is everything. And we have this map pi, which sends an element in X to the element of the partition that contains it. And we defined a quotient topology, on P, which says that U subset of P is open if and only if the preimage in X is open. And we proved a theorem last time that if Q is a quotient map, and P is the associated partition, Well, yeah, so let me just write it out, remind you. So this is the partition consisting of pre-images of points of y. Then P with its quotient topology is topologically equivalent to y. Okay, so now we're in a position to use this since we know how to recognize quotient maps. So let's see some applications. So the first one is, so let's take x to be the interval 0 to 2 pi, and p the partition, so we have this last time, so we have a singleton x for every x in the open interval, and then we have an element of the partition which has 0 and 2 pi. So now the claim, and there's not much room, so let me fit the claim here. The claim is that P with its quotient topology is topologically equivalent to S1, right? So, well, okay. So the proof is, well, let's consider. So the strategy is to find a quotient map whose induced partition, so consider we want to map from X to the circle, which is a quotient map, and so that the induced partition is exactly P. So let's consider the map Q, which is Q of X is e to the ix. So this is a quotient map simply because it's surjective, and well, X is, let's see, we're using the corollary. X is compact, and the circle is Hausdorff. That's fine. So this is a quotient map automatically. And the partition, well, let's think about how this map works. I mean, we're sending every, so the point 1 here has 2 pre-images, 0 and 1, and every other point has exactly 1 pre-image, like this. So that is exactly this partition. Every point on the circle other than the point 1 has pre-image just a singleton, and then the point 1 has pre-image 0 and 2 pi. So the associated partition is P. And so the theorem tells us that P is topologically equivalent to the circle Y. Okay, great. Let's do another example. Example 2. So here's another example from last time. So we take X to be the closed disk. View this as the closure of the unit ball in R2. And we take the partition P to be, so we have a singleton for I want to call this X, not Z. Okay, so we have a singleton X for points in the interior here. And then we have the set of all points on the boundary, which I guess I could write x minus b1 of x, or 0. So these are points. This is the circle on the boundary. Okay, so we have the closed ball, and then all the points on the boundary are in the same element of the partition. Okay, and so the claim is that P with its quotient topology is topologically equivalent to the two-sphere. So you collapse this boundary to a point and you get the sphere. So again, let me remind you that the strategy is to find a quotient map Q from X to the sphere, X is the disk, who's associated with associated partition P. Okay, so step one, we'll proceed in a couple of steps. So first of all, right, so the first observation is that the open ball around the origin, radius 1, is topologically equivalent to R2. And well, there's various ways to see this. So one way to see this is, so first note that there's a topological equivalence between the open interval 0 to 1 and the interval 0 to infinity. I think I gave this example before. Well, there's different possible choices, but one thing to choose is f of x is x over 1 minus x. So the graph of this looks like this. So this is a topological equivalence. And then, well, one can define h from the ball to R2, which I guess it'll be convenient to think of this as the complex numbers, by sending a point written in polar coordinates r e to the I theta to f of r e to the I theta. Okay, so what this is doing is you have the ball, the open ball, and well, each line, so this is, sorry, let me try this again. You have the ball and, well, that's not a line through the origin. Well, yeah, let me say it this way. This is a copy of the open interval up to topological equivalence, which is equivalent to the whole line of points forming angle. Oh, no, this isn't even what I want to say. Sorry. Sorry, so the ray in some direction is topologically equivalent to the ray where you only go distance at most 1. And so then you do this on every ray, and that gives you a topological equivalence from the ball to all of R2, or the complex numbers. Okay, so that's the first step. It's maybe not so clear how we're going to use this, but let me just tell you the steps and then you'll see how they fit together. Okay, so let me put step 2 here. So, okay, so step 1, let me just write it again so we can have it here. Step 2 will be quicker. So step 2 is something we've seen before, which is that R2 is topologically equivalent to the sphere minus a point, which I'll call infinity, and this is stereographic projection. So the picture is, we have the 2 sphere and the point, the North Pole, I'm calling infinity, and then stereographic projection is a map like this. Let's call it H or G. Okay, and that's a topological equivalence. Okay, and now putting these two together, in step 3, we define the quotient map, or map which will be a quotient map, from X to S2 by X goes to, so X is a point in the disk. If it's in the interior, it's in the closed disk. If it's in the interior, then we do the composition of G and H. H was the topological equivalence here. So H takes us into R2, and then G takes us to the sphere minus infinity. And then if X is in the boundary, then we define Q of X to be the point at infinity. So the main thing we want to show is that, so let me list this as an exercise. Q is continuous. But let me explain why you should believe this. So, well, continuity is clear away from points in the circle because G and H are continuous maps, and so then you just have a composition of continuous maps. So the thing you need to explain is why if you take a point near the circle in the disk, so let me draw the disk again. So suppose you have some point like X naught here. You want to say that if X is near X naught, then Q of X, so X naught maps to infinity. This is Q. You want to say that F of X, where F is Q, sorry, is near infinity. That's what continuity means here. And the reason is, well, if X is near X naught, then under H, X maps to somewhere far out in R2. If you've tracked the definition of H, this is what's happening. And so then H of X is somewhere far in this plane here. Let me draw it bigger. And then under stereographic projection, the farther you are away from the origin in R2, the closer you map up near infinity. Okay, so this is roughly why you should believe the map is continuous. And okay, so now we conclude. Well, the partition of P, well, let's think about how it looks. So we're looking at Q inverse of Y for Y in S2. And if Y is not infinity, then Q inverse of Y is a single point, because Q is a bijection on away from infinity. And otherwise, if Y is equal to infinity, then Q inverse of Y is S1. Okay, so the partition that we get is exactly P, this partition that we started with. Okay, so it's a little cramped down here, but the conclusion from this is this proves the claim. Okay. All right. So now I want to give you another example of quotient spaces. Let me start this as a new section. So this is the projective plane, which is a new example for us. So the projective plane, which is denoted RP2, this is defined as a set. It's the lines through the origin through 0 in R3. Okay, so you have R3, and you just look at the set of all possible lines through the origin. And we want to make this into its topological space. So to topologize this, we'll use quotient topology. And we do that as follows. So let's let X, so we need to choose X and then choose a partition. So X is going to be R3 without the origin. And the partition P will have elements of the form CV. So for each vector in R3 non-zero, we'll define an element of the partition, which is the line through V. So here, this is C is some scalar, non-zero. Okay, so this is, the partition is the collection of all of these, which is exactly the set of lines through the origin. Here, this is a line through the origins, this set here. And as you range over all possible non-zero vectors, then you get all the lines through the origin. And so this is, as a set, this is the same thing as RP2. And so then now we know how to topologize it. We give it the quotient topology. Yeah, so a bit of notation, which I guess maybe won't come up so much today, but next time we talk about the projective plane, we'll use it. So we write x, y, z in this colon bracket notation as a point in RP3. This is the, or RP2 for the line through the point x, y, z. So with the understanding that if we multiply all the coordinates by some scalar, so ax, ay, az, this is the same point in RP2 as x colon y colon z, since these two determine the same line for any scalar a. Okay, so I want to give you two different ways to think about. So here's two alternate definitions of RP, of the projective plane. You can never have too many definitions for one object. Every definition has its own advantage. So the first one, so observe that there's a surjection from the two-sphere to the projective plane. Because, well, just sending a vector to yeah, I mean, if you have some point V here, then you just consider the line through V. So through the origin. So V goes to the line through V. Through the origin and V. Or maybe, I guess, the cleaner way to say this is it's span of V. And so this is a quotient map. Again, by the proposition, so S2, the two-sphere is compact, and RP2, well, you can show that it's Hausdorff with its quotient topology. That's not so hard. Maybe I will give you that as an exercise at some point. So the induced partition, so that gives some description of RP2 as a quotient of the two-sphere. And so then you can ask, what is the partition? Of S2, it's, so P, well, the elements of the partition have the form, well, the question is, given a line through the origin, how many points does it hit the sphere? And well, it hits the sphere in 2 points, and those are V and minus V. So for V in S2. Okay, so then we conclude that so RP2 can also be described as the quotient of S2 obtained by identifying antipodal points. V and minus V. Okay. Okay, so this is another way to think about RP2, or the projective plane, as a quotient of the two-sphere. We can also think of the projective plane as a quotient of the disk. So the second description, let's take X to be the points in the two-sphere whose Z coordinate is greater than or equal to 0. So this is topologically the same as the disk. So the picture, we're just looking at points on the sphere with positive coordinate. And again, there's a map, a surjective map from X to RP2, sending, well, V to span V. And, well, the key, it's the same map, but the key is that this map is surjective. It's still surjective, and that's simply because any line through the origin will intersect the upper hemisphere in some point. Possibly two if the line is actually in the XY plane. And so the associated, so this gives us a description of RP2 of the projective plane as a quotient of the two-dimensional disk. And what exactly is that quotient? So the partition, the associated partition of the two disk. So I guess I'm identifying, so associated to this map, this quotient map, is, so it looks like this. Well, if you're in the interior of the disk, let's see, if you have a line through the origin which hits this disk in its interior, then it does so in only one point. So you have points X, or maybe I should say V, let me say X for a point in the disk. So X is in the interior of the disk. I'll write like this. Or let me write it this way. This is what I have in my notes. So if X squared plus Y squared is less than 1, then this point is in its own element of the partition. And then if you're on the boundary, then if you have a line in RP2 that is contained in the XY plane, then it hits X in 2 points. So, and those points are antipodal. So X, Y, and minus X minus Y belong to the same partition element if X squared plus Y squared is 1. So then we get this description of, so then the projective plane is a quotient of the disk pictured as follows. So we have the two-dimensional disk, the closed disk, and we identify antipodal points. So this segment here gets identified in the upper hemisphere, gets identified with the segment in the lower hemisphere, but in an antipodal way. So like this point is this point, and this point is this point. Okay, which I've indicated by the fact that the arrows are not pointing in the same direction. Or they are pointing in the same as you go around. And so this space, I think, should look familiar. This is the two-dimensional disk union a Mobius band. If you cut this up, so you have like an interior disk here, And then the outside here is a Mobius band. And so in our classification of surfaces, this is the surface we called N1. You remove a disk from the two sphere to get a disk, and then you glue a Mobius band along the boundary. So this, I think, came up in homework 3. Okay. All right, one more topic for today. Which I want to continue saying a little bit about. Well, last time we talked about topological groups. And so this is a continuation of that discussion, group actions. And I think next time we'll see some connection of this topic, which seems disjoint from quotient spaces, but we'll see some connection to quotient spaces. So the definition of a group action, so let's take G, a group, and X, a space. So a group action is a homomorphism from G, let me call it phi, from G to the group of topological equivalences of X, which I defined at the end of lecture last time. Which is to say, so i.e. for each group element, G, little g, we have a topological equivalence phi of G, which is a function, so it's a topological equivalence of X. So it's a function X to X. The fact that this is a homomorphism means that, well, phi of G compose H is phi of G compose phi of H. And this implies, in particular, that phi of the identity of G is the identity function on X, the identity of this group top X. And well, okay, so one point of view is, well, the whole reason groups exist to some extent is to be symmetries of spaces. And so a group action is some group of symmetries of a space. And I'll show you some examples in a second. Yes. Another point of view on this is, so we can view this a group action as a multiplication of sorts. Which is to say, well, it gives us a function, G times X into X. So if you're given a group element G and a element little x in X, then, well, there's some new element of X, which you might write as G times X, which, well, this is sort of a shorthand for this longer notation of the topological equivalence associated to G acting the value of that evaluated on X. So that's what this notation means. Yeah, okay. So I want to get to some examples, but first a remark. If G is a topological group, well, then we probably also want phi to be continuous. So if G is a topological group, the group of topological equivalents is also a topological group. I mentioned this briefly last time, and so it's reasonable to ask for this map to be continuous. And this will be true in all the examples that we look at, and so we're not going to worry about this sort of thing. Yeah, the main thing I want to communicate is examples, since this is what makes things interesting. So examples. So the first example is kind of has no topology. So suppose X is a finite set with the discrete topology. Then top X, well, this is equal to the symmetric group. It's just all the permutations of 1 to n. So this is all bijections from 1 to n to itself, which is also known as AKA a permutation. And so a group action on X is just a group of permutations. So group action on a finite set. This is, so okay, I am giving you this example to explain the point of view that group actions are like symmetries. So symmetries of a finite set are just permutations, and more generally, group action is symmetries of some space. So some more interesting examples. So G is Z acts on X is R by translations. So in notation, well, if n is some integer and x is some real number, then the action is x goes to x plus n. So the way this acts on the line is, well, you just shift everything. So, okay, you have things just get shifted by n. You shift every point by n. Okay. Okay, second example. I guess this is a third example. G is GL and R acts on X is Rn by linear transformations, linear maps. I mean, this is, yeah, I mean, so like A, B, C, D, this is an invertible matrix acting on a vector in the usual way by matrix multiplication. And this is a group action. And then the last example I want to mention is if we restrict to the orthogonal group. So these are linear isometries. This acts, well, it acts on Rn, but it also acts on the sphere. So vectors in Rn with norm 1. by restriction of the same action. Of course, you know, the action of a general, you know, invertible matrix won't necessarily preserve the sphere. I mean, it sends the unit circle to, so in the 2x2 case, it sends a unit circle to something more like an ellipse. But if your matrix is orthogonal, is an isometry, then it preserves distances. So it sends the unit sphere to itself. And so this will be an interesting example to think about. Okay, so let's stop here for now.